So is my lecture slide visible to you?
Yes, sir.
Okay, great. Okay, so let me start today's lecture. Okay. In my previous lecture, I think we had discussion about fatigue, cyclic plastic deformation, where basically we talked about crack initiation, crack growth, and what kind of microstructure evolution takes place during cyclic deformation. And we also had a little bit discussion about fracture mechanics, the mode of understanding the fatigue behavior of materials. So where we talked about Paris law, how the crack growth, okay, changes, changes with a stress intensity factor range. So I think afterwards we started having discussion about thermally activated plastic deformation of metals. So plastic deformation is considered as a dynamic process. Okay, it basically time dependent process. So in 1925, Becker was the first one who has recognized the concept of a dynamic nature of plastic deformation, time dependent plastic deformation nature. Okay, so if we apply some thermal fluctuations that can assist the stress, okay, that means if the temperature is higher, usually the stress requirement is going to be lower for the plastic flow in a materials. So according to Becker, he used Arrhenius type of equation to describe strain rate. Okay, the rate of deformation is basically going to depend on temperature. Okay, is a temperature can assist the rate of deformation, and there is a term called enthalpy, also called activation enthalpy or activation energy, is basically also going to depend on stress. It usually decreases with the applied stress. So in materials, typically we do see two types of barriers, okay, thermal barriers and thermal barriers. Thermal barriers are long range stress field, which basically have a at least 10 atom diameters of size. The size of the barriers will be greater than 10 atomic diameters. For a those are called long range. Those can create a long range stress field. Those barriers are called athermal barriers. Those barriers are called athermal barriers. So we do see very short obstacles, which are of size less than 10 atomic diameters. So those can lead to short range stress field around those barrier. We do see short range stress field. So these short range stress field, whatever is there, the barriers around the barriers. So those barriers are called thermal barriers. So thermal barriers can be overcome. We can overcome those thermal barriers, by applying some thermal energy. By increasing temperature, we can actually overcome some amount of some of the barriers. Those barriers are called thermal barriers. Thermal barriers, the temperature change will not affect your thermal barrier. That means actually the stress required, the total stress required for a plastic deformation to take place is basically, if I talk in terms of a shear stress, total shear stress required for plastic deformation is basically summation of the stress required for overcoming thermal barriers and stress required for overcoming thermal barriers. So thermal barriers is basically the stress required for thermal barriers is going to decrease with increasing temperature. Similarly, with the decreasing strain rate also, the stress required for at a given temperature, the stress required to overcome thermal barriers at low strain rate is low, as compared to high strain rates. So the strain rate and temperature dependent is basically there for the thermal stress component. Okay, so we have discussed some important thermal barriers, which basically come. Okay, when you talk about the thermal barriers, it can be a overcoming of Piles-Navarro stress, intersection of porous dislocations. Okay, these porous dislocations basically can be overcome. We can overcome these porous dislocations by giving us some thermal energy. Similarly, okay, non-conserved motion of jogs, which basically pins the dislocations, those can be overcome by applying some thermal energy. Similarly, cross slip and a climb. So these are important. Cross slip and climb are important. Okay, high temperature deformation rate controlling mechanisms. Okay, high temperature rate controlling mechanism, which can basically, which means that by giving some thermal energy, we can make cross slip very easy. Similarly, climb also can be happen very easily with temperature. So these are actually important thermal barriers which can play significant role during plastic deformation of materials at elevated temperatures. Is it clear? I think then actually we had, I think, discussion, some definition about a activation volume, because initially we had a activation energy, it's also called activation enthalpy, and activation volume, another concept which also related to the amount of dislocation activity is acting. The volume representation of a dislocation activity is represented in the form of activation volume. This basically nothing but activation volume is basically how the enthalpy changing with stress, that is called activation volume. The change in enthalpy with stress is called activation volume. So depending on type of barriers what you are talking about, so the rate controlling mechanism, if we talk about, these are different type of rate control mechanisms. So depending on rate control mechanism, the activation volume is also going to vary. If you talk about climb, the amount of total dislocation activity what you see is a very small 1 BQ. In case of a cross slip, typically we see 10 to 100 BQ. Other things basically higher volumes are involved. The total dislocation activity will be more. In case of non-conserved motion jogs, intersectional dislocation, where actually the total dislocation volume will be more. So this basically, I think I stopped it at this slide. If there are any doubts, please let me know. In my previous lecture, I think I stopped on this slide. So if there are any doubts, we can have a discussion on them. Otherwise, I can proceed further. Any doubts? Hello, am I there?
Yes, sir, you are audible, sir.
Okay, because some network issues are coming daily in the department. Sometimes suddenly, logging out, from the Google Meet. Okay, so if it is not clear, I think let me see. Let me proceed further to have some more understanding about thermal activation of plastic deformation. So we had discussion. I think we know. Diffusion is expressed using a Arrhenius type of equation. D is equal to D naught exponential minus Q by RT, or sometimes people say delta H, or simply H by RT. D is the diffusivity, D naught diffusion coefficient, Q or H is a activation energy, R is a gas constant, T is the temperature and absolute scale. So we do see different types of diffusions. Different types of diffusions in materials. So can anybody name some different types of diffusions what we encounter in materials? Different types of diffusivities. Any idea? Different types of diffusivities what we see in crystalline materials.
Self-diffusion,
Diffusion?
sir. Self-diffusion.
Self-diffusion. Okay, self-diffusion. Okay, you're right. Okay, what is meaning of self-diffusion?
So there is the atoms in a material, they diffuse without any after the application of thermal energy, they diffuse in within them with vacancies.
Yeah, if we take it same atoms, same type of atoms, if it has to jump from one block position to other position, there will be some activation barrier. There will be a barrier, so one has to overcome that barrier. So that requires some activation energy. So that activation energy is called self diffusion. Activation energy for self diffusion. So that whole thing, the same atom jumping from one atom position to other atom position, that is called self diffusion. That's the one thing what we see in materials. Anything else or any other diffusivities what we see in materials, crystalline materials?
So grain boundary diffusion.
Yeah, diffusion along grain boundary, that's typically called DGB. Yes, diffusion through lattice. Okay, typically diffusion through lattice is almost approximately equal to diffusion self-diffusivity. Okay, in case of pure metals, okay, diffusion through lattice is approximately equivalent to self-diffusion. Okay. Any other things would you see other than, okay, now self-diffusivity, lattice diffusivity, diffusion through lattice, diffusion along grain boundary. Anything else do you see? Because this, okay, diffusion through lattice, diffusion through grain boundary, we talk in terms of polycrystalline materials. Okay. If it is a single crystal, only we talk only diffusion through lattice. Okay. Any other thing do you see other than these three? Any idea apart from these three? No. Okay. If there are a lot of dislocations, okay. So dislocations, okay, core can also contribute to the diffusion. Diffusion can also take place through the diffusion core. Okay, that's called pipe diffusion. It's also called core diffusion. Core diffusion or pipe diffusion. Okay. So if we talk about in a polycrystalline material, okay, we do talk about diffusion through lattice, diffusion through along grain border, diffusion along grain borders. So according to this equation, Arrhenius type of equation, okay, if I make a plot, log D versus 1 by T, okay, typically we get a, okay, line, okay, like this, okay, data points for, okay, in the, here. So the slope, okay, the slope basically gives you, okay, activation energy. For example, okay, if I take, okay, if I take this DL, okay, this is the DL, okay, and this is the DZB, okay, the slope, the respective slope will give you activation energy for, okay, diffusion, okay, through lattice, activation energy for, okay, along the, okay, diffusion along the grain boundaries. So we'll have a, okay, QGB and QL. Okay, respectively we'll have a QGB and QL. Am I right? Okay. If a norm, okay, now for example, I have two, okay, these two, okay, in a polycrystalline material, both of them are going to take place. Both of them are going to, okay,
Sir,
diffusion. Yes.
sir, there is a lot of background noise coming from your end. I think it's your earphone that is making the noise.
Mm, still, I'm getting still, just 1 minute, just.
It's okay now. Sir, you're on mute
You
now.
are muted, sir. No, sir, we are not able to hear.
Sir, you're on mute.
No, sir. No, sir.
No, sir, you're not audible.
Close and come again, sir. It's better.
Hello.
Yes, sir. Now it
Yes,
is.
sir. Now,
Okay.
You are audible.
Yeah, I'm sorry. I think there's something went wrong with my mic. Let me share again my lectures. Is my lecture slide visible now?
yes, sir.
Yes, sir. It is.
Okay, thank you. Yeah. So basically, we are talking about different types of diffusivities what we see in crystalline materials. Okay. So we do talk about self-diffusion. Okay. We do talk about lattice diffusion and grain boundary diffusion. And okay, the last one is a pipe diffusion. Four different types of diffusivities we do encounter in crystalline materials. Okay, so according to this Arrhenius equation, if we make a plot log d versus 1 by t, we do get a okay, that line will be linear. Okay, line we get the slope will give you respect to okay. Typically, we talk about lattice diffusion, grain boundary diffusion. We do get a okay. The slope okay will be what we get is a q by r. Okay, so from that we can get a q. So activation energy for okay diffusion through lattice, activation energy for okay diffusion along grain boundaries. Okay, so in polycrystalline materials okay diffusion takes place through the lattice as well as along the grain boundaries. However, okay, the dominant diffusion is going to be okay depend on temperature. What type of diffusion is going to be dominant is basically depends on temperature. Okay, if it normalize okay this dgb with a grain boundary thickness and the grain size. Okay, if we take dgb we multiply with delta by d. Okay, this comes okay down here. Okay, so there we do see two intersection. Okay, we do see intersection. So what is the effective when you talk about effective diffusivity? Okay, effective diffusivity okay, when it's a lattice okay through the lattice and along the boundary. So effective or apparent diffusivity typically represented okay like this equation. Okay, if I normalize okay, okay dgb with delta by d. Okay, that gives you like this. Okay, so there is a transition. Okay, above that transition okay we do see okay diffusion happens okay through the lattice. Okay, so okay below the transition, above the transition what we see diffusion okay along the grain boundaries. Here look at here, this is 1 by t, your x-axis is 1 by t. What does it mean here? If we take this as a transition okay, so at high temperatures we do see okay the dominant okay thing is basically diffusion through the lattice. At low temperatures, we do see diffusion through grain boundaries. Okay, along the grain boundaries is the rate controlling thing. Okay, is it clear? So this is how actually we'll come to know at what temperature. Okay, okay at a given temperature. Okay, what type of diffusion is going to be the rate controlling? Going to be the rate controlling. Okay, so if you take a polycrystalline materials at low temperatures, typically okay diffusion through okay, along the grain boundaries is the one has to consider. Okay, among the effective diffusivities, so this is going to be dominant. Okay, at low temperatures. At high temperatures, lattice diffusion is going to be dominant. Similarly, okay, we do talk about okay when you talk about pipe diffusion, there also, for example, there is a pipe diffusion and lattice diffusion both. Okay, so which one is going to take place? Okay, so one can actually get a apparent okay value okay apparent diffusivity by considering lattice diffusion and pipe diffusion. Okay, if you normalize it accordingly, we'll come to know at low temperatures we do see pipe diffusion is going to take place, whereas at high temperatures pipe diffusion through lattice is the dominant thing. Okay, so this is how actually we do okay understand about the diffusivity. Okay, why I'm talking about diffusivity? Because we said plastic deformation is a thermally activated process. Okay, when you talk about thermal activation, we have to know diffusion. Okay, we have to have some understanding about diffusivity. Okay, that was the intention of showing this slide. Any doubts here? Are there any doubts? Hello,
Sir,
am I
this
there?
sir,
Yes,
this
sir.
D effective, that point I did not get, sir.
No,
What
you can
is
see in polycrystalline materials, if you take a polycrystalline materials, okay, we do see both grain boundaries and grains also. So in polycrystalline materials, what is actual total effective diffusivity we are going to talk about. Okay, the effective diffusivity we have to consider both diffusion through the lattice and along the bond. Both you have to consider. Okay, however, which of them is going to be dominant? Basically, the rate controlling thing. How do you know the rate controlling? Okay, how do you know rate controlling mechanism? Any idea? How, for example, there are two processes happening. Okay. Now we said, okay, in polycrystalline materials, we will know there will be lattice diffusion, also grain boundary diffusion. Which of them is rate controlling? How do you know? Any idea?
Which which is the slowest uh, process? That one is the red reaction.
Yeah, is it always slowest one is the dominant always?
Yes, sir.
Always. For example, okay, you have a two processes, okay, which are actually can happen sequentially, can also happen parallel simultaneously. For example, okay, we have okay process. In these two processes may happen sequentially, can also happen parallel simultaneously. In a sequential thing, the slowest one is the dominating one. Okay, in a sequential process, if the two processes are happening in sequential manner, then slowest one is the dominant. If both of them are happening parallel simultaneously, okay, the fastest one is the rate controlling mechanism.
Yes, sir. Yes.
Okay, the fastest one is the rate controlling mechanism. For example, here lattice diffusion, grain boundary diffusion, these are interdependent. Okay, this will not depend on each other. These are parallel, simultaneously can happen. But which of them? Okay, you have said these are parallel processes. Okay, simultaneously can happen. So fastest one is the rate controlling mechanism. Fastest one is the rate controlling mechanism. If you look at here, okay, this is the lattice diffusion, and this is actually grain boundary diffusion as a function of temperature. Now below the transition, okay, below this is a transition. Now we are crossing. Okay, below the transition, the fastest one is the dominating one. Higher diffusivity one is the dominating one. Okay, look at here. So this slope, what you are seeing, okay, corresponding to this one. Fastest one is the rate control. Okay, above the transition, okay, what is dominating one? Grain boundary diffusion is the dominating one. Okay, so this is the the slope basically changes here. Okay, this is the my effective diffusivity. Okay, is it clear?
yes, sir. Yes.
These two are
Yes, sir.
actually independent. These are two are independent process. Okay, not a sequential process. So independent process. Okay, we do talk about fastest one is the rate controlling mechanism. Okay, so this is how actually people come
Sir,
to. Yes.
so what is the difference between the two formulas? D effective you have put two times. So what's the difference between the top and bottom one?
Which one? The bottom one is actually pipe diffusion. It considers pipe diffusion. Here, grain boundary diffusion. Okay, we are not considering pipe
Okay.
diffusion in this case. Okay, we are considering pipe
What is
diffusion.
pipe diffusion?
Pipe diffusion is a dislocation. Okay, can also contribute to diffusion. The atoms can diffuse.
Okay.
Okay, in the through the diffusion core, dislocation core through the dislocation core. That is called pipe diffusivity.
Okay, sir.
Okay. So typically, the activation energies per lattice diffusion is almost close to a self diffusion. Activation energy for grain boundary diffusion, okay, it's about zero point 0.5 zero point 6 times of around 0.5 zero point 6 times of a self diffusion. Typical values, okay, it's approximately 0.5 to zero point 0.6 times. Okay, similarly pipe diffusion, it also we talk about the activation energy for pipe diffusion also comes around zero point 0.6 times of okay, zero point 0.6 times of the self diffusivity. Okay, the activation energy for self diffusivity. Okay, typical values. Okay, it's like ballpark numbers what we see. Okay, the activation energies. Okay, that means actually activation energy for through the lattice is going to be higher. That means actually barrier size is bigger. Activation energy required for the diffusion along the grain boundaries is relatively easier because your diffusivity is actually small, low. The activation energy for diffusion is low. Okay, similarly activation energy for pipe diffusion is also low. Okay, that means diffusion can happen quite easily. Okay, So whenever there is an open space, whenever there are defects like these locations, we'll basically enhance the diffusivity. Enhance the easy, basically diffusivity can happen very easily as compared to through the lattice. Okay. Is it clear about the diffusion?
Yes, sir.
Yeah, there's a huge science, okay, behind this diffusion. There's a separate course, okay, one can actually have. But as far as this course content is required, I'm giving some important, okay, terminologies which you have to understand. Okay.
Sir,
Yes.
so why not the pipe diffusivity is also considered in the plot?
Which one here? Which plot? Here actually you can consider. That's what I'm just giving example for this thing. Okay, between line boundary and lattice. Like that. Okay, we'll also have a lattice diffusion and pipe diffusion. Also similarly we'll have. You have to normalize. Okay, you have, it also, for example, if you take a DP, you may get somewhere. Okay, so that also has to be normalized with this AC. Okay, this one you have to normalize with this thing. Okay, then also normalize with G, sigma by G square. This you have to normalize. Then only we'll come to know what is the fastest one, okay, correct control mechanism. Okay. So this is actually example for this one. Okay, I've given example for considering DGB and DL. Okay. Similarly, one can also consider DP and DL.
Okay, sir. Okay.
In this case, you have to normalize with this parameter. Okay. If you normalize, then only will come to intersecting things will come. Then we'll come to know which is the rate control. Okay. Typically, high temperature always, okay, at high temperatures, okay, the high temperatures we do see lattice diffusion is the rate control mechanism. Okay, at low temperatures, either grain boundary diffusivity or pipe diffusivity are the rate control mechanism. Okay. Okay, this is only in terms of a temperature effect. Okay. We are talking temperature can play a role for the diffusion. Okay. So that means once you go to higher and higher temperatures, diffusion is important concept. Okay. Diffusion of atoms have to be considered. Even when you apply stress, okay, at high temperatures, okay, we are talking about diffusion has to also be considered for the plastic deformation of the materials. So here, typically, the activation energy, okay, the activation energy. If you talk about only, I'm talking about only self-diffusion. Self-diffusion. Okay, here only the y-axis is self-diffusion and melting temperature. Okay, higher the melting temperature, higher the activation energy of self-diffusion. I'm talking about self-diffusion. Okay, that means actually, if you talk a low melting point material, aluminum and tungsten. Okay, so which is having low atomic activation energy. So obviously aluminum. Okay, according to this plot, it basically shows lower melting point materials will have a lower activation energy for their self-diffusion as compared to high melting point materials. Okay, so it's basically depending on melting temperature. Okay, the diffusion also going to vary. Okay, higher melting point can lead to higher activation barrier. Okay, that means you need to have a very high stress or high temperature to then only can see activation of diffusion take place. So if I take this plot, okay, there is a kind of the slope typically, okay, if I correlate between the activation energy for self-diffusion, QSD, simply called QSD or delta HSD, or simply H, some people also use HSD, is basically related to melting temperature. The approximate value is about 160. About 160. Okay, so the activation energy for self-diffusion is about 160 times of the melting temperature. Okay, the units will be joule per mole. Okay, if I use 160 multiply into melting point, okay, the energy activation energy comes in a joules per mole. Okay, typical ballpark number. Okay, so based on this, people have come up with a relationship between activation energy for self-diffusion with respect to melting temperature. Okay, it gives you 160 times of melting temperature. So the units of the energy will be joules per mole. Okay, so I said, okay, depending on temperature, okay, the diffusion can be lattice diffusivity, or can be a grain boundary diffusivity, okay, or depending on dislocation density. If there's a lot of dislocation density, we also talk about pipe diffusivity. Okay, so if you look at here, some kind of 3 different materials are considered here. Okay, so aluminum FCC, iron BCC, magnesium, okay, is the HCP. Okay, so typically, if I look at how the activation energy for plastic deformation, activation energy for plastic in polycrystalline materials, how it changes as a function of normalized melting temp, normalized temperature. When I say normalized temperature, T by Tm, it's called homologous temperature. The ratio temperature, test temperature at deformation temperature to melting temperature on absolute scale, it is called homologous temperature. So look at here, typically we do see, the activation energy is going to change, activation energy for the deformation is going to change depending on at what temperature deforming, at what temperature you are heating the material, accordingly your activation energies are going to change. So when you talk about high temperatures, we do talk about lattice diffusion. That lattice diffusion basically almost close to your self diffusion, self diffusivities of the materials. At low temperatures, we do see grain boundary diffusion or pipe diffusion going to be rate controlling process. Is it clear? Any doubts here? So accordingly, the rate controlling mechanisms, are categorized into different types, depending on temperature. The temperature less than 0.25 times of melting point. So we call low temperature. 0.25 times of melting temperature to 0.5 times. Times of melting is typically called intermediate temperature domain, and high temperature domain basically temperature greater than 0.5 times of melting. So look at it depending on crystal structure. The type of rate controlling mechanism, the most likely rate control mechanism can also vary slightly. Look at here. If I take a FCC material, aluminum, at three different temperature domains. Three temperature domain. Here, look at here. At low temperature, intersection of dislocations is the rate controlling mechanism. That means what we are considering, these are all thermal barriers. When you talk about temperature, we are talking about only thermal barriers here. So intersection of dislocations are the rate controlling mechanism at low temperature. If we go to intermediate temperature, I do see actually the rate control mechanism is cross slip. If we go to high temperature, climb is the rate control mechanism. See, look at it, the rate control mechanism changing depending on at what temperature you are deforming the material. Low temperatures, intersection dislocations, intermediate temperatures, cross slip, high temperatures, climb. I'm just giving one example. Look at it, people have come up with what type of mechanism can be a rate control mechanisms when you deform material at certain temperature. Is it clear? Any doubts? Yeah. Any doubts? I think, is it clear about type of rate control mechanism? Because these are all what we are talking about, thermal barriers. So which thermal barriers basically control the plastic deformation of a material. So if we talk about there are two ways we can deform the material. Either you can maintain constant stress or a constant strain rate. As a function of time, I can maintain constant stress or constant strain rate. If I maintain constant strain rate, typically what you talk about tensile compression, axial testing. Typical axial testings involve constant strain rate. Creep testings involve constant stress. So accordingly, your stress strain curves are how the your strain is changing, how the stress is going to change is going to vary depending on what type of variables you are maintaining. We are trying to vary the variables. So if you look at here, if you do a tensile test, at low temperatures, around room temperature or below room temperature, typically we do see a work hardening. If we do a tensile testing, we do see a stress strain curve. If we take a stress strain curve, here how the stress is varying as a function of time. Just I'm talking about only how the stress is varying as a function of time. We do see a work hardening in the material. In case of a creep testing, if you maintain constant stress at low temperature, initially there will be slight increase in strain. There will be some amount of strain. Afterwards, you see we don't see much change in the strain. If you make a strain rate, how the strain rate changes? Strain rate slightly increases, then comes down, becomes 0. typically at low temperature. If you go to high temperature, okay, 0.5 times the melting point or 0.9 times the melting point, okay, under tensile testing, we may see a steady state kind of behavior. The stress, okay, may attain some steady state. You may see dynamic recovery, or we may also see some dynamic recrystallizations can be seen, okay, when you do deformation under tensile testing, where you are maintaining constant strain rate. If you maintain a constant stress, which basically creep testing kind of thing, okay, we do see, okay, creep curve. Typically, you get a creep curve, strain versus a time, or you can also convert them to strain rate versus time. Okay. Typically, we get some stages in a creep curve. Okay. If you go to very high temperatures, we may see some kind of wavy nature of a creep curve. Okay. So some kind of quasi steady state may be attained. Okay, but there will be a lot of, okay, waviness because of a dynamic recrystallisation can take place even during creep deformation. So this is basically what I'm talking about. So depending on temperature, at what temperature you deform material, and how you're, okay, what type of variable you are maintaining. Okay, are you maintaining, okay, constant strain rate or a constant stress? Accordingly, okay, depending on temperature, the type of, okay, behavior is going to vary. Okay, is it clear? Any doubts here? Okay. So, okay, I want to, okay, discuss something about activation volume and activation energy some more. Okay, here. So we know that, okay, we do see barriers, different types of barriers. Am I there? Am I online? Hello.
Yes, sir.
Yes, sir.
Fine. Yeah. Sorry. Once in a while, need to ask. Okay, otherwise, okay, I'm just I won't be able to see you. Okay. Here. Okay. So what I'm talking about, in a material, will have barriers, thermal barriers. Okay, the total stress is basically combination of, okay, the stress component, okay, related to, okay, a thermal and thermal component. Okay. So if I take, for example, okay, I said when I give some thermal energy, I can overcome, okay, I can overcome some amount of a thermal barrier. Okay, if I just take, okay, my just only thermal barrier, because I'm giving some energy by thermal energy. Okay, so for example, if we take that, okay, this particular, okay, thermal barrier, okay, in terms of a force versus, okay, distance, force versus a distance. Okay, so if I take only that one, okay, assume that, okay, I have given a stress, okay, beyond, okay, tau mu. I have given a stress, I have applied stress, okay, externally beyond tau mu. Okay, but less than, okay, total tau required. Okay, the total tau, okay, this is actually total tau. Okay, so total tau basically tau mu plus, okay, tau mu plus, okay, tau star, it's total tau star. So the tau naught, I'm applying a stress which is greater than tau mu but less than tau naught, less than tau naught. Okay, that means actually I'm applying, okay, I applied already some amount of stress, then it's already crossed some amount of barrier. Okay, I'm applying stress, okay, the dislocation, okay, we already crossed from here to here, assume that. Okay, now, okay, if I have to, okay, I need to apply very high, okay, stress, so that this can overcome this barrier, come, okay, deformation can happen, or I need to give a some additional some thermal energy, so that actually I can overcome this thing. Okay, there are two things basically, either I can increase the stress further so that I can have a tau naught, okay, or I have to, if I apply some thermal energy, I can actually assume that I'm applying some thermal energy. Okay, that basically leading to a overcoming of this barrier. Okay, that means actually, okay, this is the, okay, the area under this curve is basically, okay, the thermal component what we are giving. Okay, the total energy, whatever, okay, the activation energy, if you talk about, okay, in the total activation energy, assume that this is the shaded one is basically coming from a thermal energy. Okay, so initially, okay, I'm applying a stress up to, okay, this point, so that actually, okay, I can actually overcome this much of, okay, barrier. After that, actually, I'm giving some thermal energy, which is basically leading to overcoming this. So I want to know how much thermal energy, okay, is required. Okay, what is thermal activation required? Okay, if it is a 0 Kelvin, I need to apply tau naught because there's no thermal energy. At certain temperature, I don't have to apply, okay, complete tau naught. Okay, some amount of stress is good enough, some tau is good enough. Okay, some tau is good enough. Okay, because some amount of is already being taken care, okay, by the, okay, thermal energy, because at that temperature already some thermal energy is taken up, okay, taken care. So how much, okay, this can be up, how do you get, okay, this thermal energy? Okay, so one way basically how do you get it? Because now I have a force versus a distance curve. Okay, I want to get what is the, okay, the area, okay, the work done is basically the area under the curve. Typical, the total work done is basically area under this, okay, thermal barrier. Okay, but I'm giving, okay, already some. So that this area I want to have. How do you get actually? If I take, okay, total, okay, H, okay, the H I want to know the H. H is basically I can get area under this curve. Am I right? Total area under this curve minus, okay, if I okay, minus if I do this thing, I can get H. Am I right? Is it clear what I'm saying here?
Yes, sir.
I want to determine, okay, area under this. Okay, this is work done. Okay, force versus distance. This is work done. Okay, so this I want to determine what is H. So this H is equivalent to, okay, I can take only, just take only this region. Okay, if I take only this region, so area under this curve, total area under this curve minus, okay, if I remove this portion, I get area under this curve. Okay, this is, okay, shown here. Okay, f of x, okay, x naught to x naught star, okay, x naught to x naught star, f of x, and minus, okay, I'm actually having a, okay, force. That force I'm dividing, okay, basically nothing but tau star b into L star. Okay, L star is a length of, okay, segment, dislocation segment, which participating, okay, for overcoming the barrier, overcoming the barrier. Okay, so those d star basically x naught minus x naught star minus x naught basically gives you d star. Okay, so this tau star b L star dx, so this is how actually I can get a H value. Okay, so if I do, okay, this is actually, if I take this one H star and minus, okay, this tau star b L star. Okay, this, okay, we are talking about bl star and dx. If I integrate dx for x naught to x naught star, will basically we are taking a d star. Okay, so bl star and d star is basically called activation volume. Okay, b l star and d star, okay, okay, multiply these three, that gives you activation volume and tau star, and this is actually h star. Okay, so this is actually we get a activation, okay, energy equal to, okay, activation energy only, which is basically coming, which has to be coming from thermal energy, is equivalent to h star minus b star t tau star. Okay, so this v star is basically, okay, sorry, the v star is basically is a dh by d tau, dh by tau star. Okay, how the energy is changing as a function of, okay, stress. Okay, which basically B, D star, L star. Okay, this is how actually activation volume has been defined. This is actual activation volume. But actually, if I take complete area, okay, if I take complete area, okay, if I, okay, remove this portion, this portion, this portion, these three, okay, then also I can get a H. This is another way to get a H. The H can be, okay, obtained by taking the entire, okay, area H naught minus, okay, this and these three. If I, okay, subtract, then I can also get H. So that V basically called, okay, total activation volume. Total activation volume. Okay, these are different ways to, okay, get this H. Okay, so here we're considering entire, okay, these three portions, that gives you total activation volume, but actually which is participating. Okay, if you take only this one, okay, if you subtract this thing, tau star b l star, okay, this force into d star, so this basically gives you, okay, tau star into v star. Okay, so this v star is actually activation volume, which basically involved for a dislocation segment of l star, okay, to overcome a barrier, to overcome a barrier of a size d star. Okay, how much activation volume is involved? Is it clear? It's a simple mathematical, okay, integration and subtracting to get a, okay, how much energy you have to supply, okay, to overcome the, okay, this barrier. Okay, so now, okay, we have, okay, according to, okay, we know that, okay, according to Vorovan equation, okay, which has also has come from Becker, Becker has given, okay, Becker has given strain rate. Here I'm talking about shear strain rate is equal to rho BV. Rho is the dislocation density, B is the Burgers vector, V is the dislocation velocity. So this dislocation velocity typically represented L, dislocation length, okay, nu star, okay, frequency factor, exponential minus H, okay, by KT. Okay. So this is basically nothing but what we are seeing, okay, okay, according to Becker equation in the first slide we showed, okay, strain rate equal to nu exponential H by KT, okay. So the same thing, even over equation also has been extended to represent how the strain rate is going to, okay, vary with the temperature. Okay. It's like, okay. So if I take, okay, rho B L V star as a, okay, nu, okay, we get, okay, if I do logarithmic on both sides, log of gamma, okay, dot strain rate, log of strain rate, okay, this basically take, okay, if I take logarithmic of this one and logarithmic this thing, I want to have H. So H becomes a KT ln nu gamma, okay, strain rate. Is it clear? It's a simple, okay. We have actually this kind of expression, okay, which is well-known expression. If I take a logarithmic on both sides, okay, both sides, I can arrive, okay, how the, okay, activation energy or enthalpy, okay, changing as a function of strain rate here. We just reverse the both sides. So that actually KT ln nu is a frequency factor, okay. It considers all of, okay, all these things and strain rate. Is it clear?
Yes, sir.
How? Okay, this is a simple, okay, just use logarithmic on both sides and, okay, change it other side so that I'll get a H. I want to have a H. How the H is going to change? Here, remember that it's a minus. That's why it's going to be, okay, 1 by, okay, strain rate, okay, ln 1 by strain rate, okay. So now if I want to determine, okay, my, okay, activation volume, okay, if I want to determine activation volume, what actually I know that activation volume is equal to nothing but change in, okay, enthalpy with stress, change in enthalpy with stress, okay. If I take, okay, now I have a H, if I do, okay, derivative of this thing, if I get a derivative, what is the derivative can give you? Derivative is basically KT, okay, dou ln gamma dot d tau at a constant temperature. We are assuming temperature is constant. Okay, that's one case. If we assume strain rate is constant, then if I do derivative, okay, partial derivative of this thing, okay, okay, dH by d tau will give you like this. So there are two things, okay. In case of constant temperature, your activation volume is going to vary, okay, KT tau ln gamma dot by d tau. Okay. If I assume constant strain, if I do the test at constant strain rate, okay, so that means actually if temperature actually is basically varying, okay, as a function of stress. So we do see, okay, as a function of temperature, we stress also going to vary. If we do derivative of this thing, okay, as a function of stress, okay, we do get like this. Is it clear? So if I want to determine activation volume, okay, there are two ways. Either have to maintain constant temperature and understand, okay, I establish, okay, how the strain rate, okay, okay, changing strain rate, how the stress is changing. For example, if I change the strain rate, I can get a change in stress. Am I right? If you take a simple tensile test, if I do simple tensile test at a constant temperature, okay, that means if I vary the strain rates, okay, I'll know the change in stress, okay. So that can give you, okay, activation volume. If I make this kind of, okay, thing, we'll get a strain, okay, activation volume. Or if I, okay, here actually just maintaining constant strain rate, changing the temperature, that can also give you activation volume. Okay. So the simple way, what people do some jump test. Okay, do some jump test. Here, for example, I'm talking about tensile test. Okay, tensile test will give a stress strain curve. Okay, at a temperature, I'm maintaining constant strain rate. Okay, I deform material at T1 temperature initially. Then, okay, I suddenly change the temperature. I increase the temperature, some delta T. Okay, with increasing temperature, usual stress comes down. Okay, the stress is coming down. Okay, now I have a delta sigma. Okay, for a change in temperature, delta sigma, delta T I have. Okay, so if I put, okay, my change in stress with temperature, okay, I can get a activation volume because your strain rate is constant, K is constant, okay, this is a nu also constant. So I can get a activation volume. Okay. The other way, okay, maintain constant temperature, change the strain rate. Deform material initially at particular strain rate, suddenly jump it, do some jump test. Okay, then that can lead to increase in strain rate, typically lead to increased stress in case of a positive strain rate sensitivity materials. Okay, delta sigma I have, now delta epsilon dot I have, okay, because I have change in strain rate. So if I put this, okay, value, okay, I'll get an activation volume. Okay, this is how actually people determine activation volume. This is one of the ways. Okay, there are different ways. This is one of the ways to determine activation volume. Okay. Any doubts here? Are there any doubts? Is it clear? Hello? Hello?
Yes, sir.
Okay. So this is how actually people determine activation volume. Okay. So the another thing from creep test also people do. Okay. I think from creep test also people can determine activation volumes or activation energies. Okay. So typically if I take H is equal to minus K, okay, if I do at a constant stress, creep test typically will be done at a constant stress. Okay, you can also get activation energy. From that you can also determine, okay, because you're deforming material at constant stress, okay, you can also get your activation volume also, because dH by d tau. Okay, so research from creep test people determine activation enthalpy or activation energy for deformations. Okay, so these are simple equations we use from the basic equation we can actually get this enthalpies. So from creep test typically we usually do constant stress, and do a jump, temperature jump. Okay, so if I have now actually from the temperature jump, when you do temperature jump, we do see change in strain rate. Locally do see a change in strain rate when you change the temperature. So by using that change in strain rate as a function of change in temperature, we can get a activation enthalpy. Okay, so look at it, dln gamma dot d1 by t. Basically here we're talking about a true strain rate, dln epsilon dot d1 by t. Okay, if you get this value, I can get a activation energy or activation enthalpy of the deformation. Similarly, constant temperature, if I maintain a constant temperature, okay, so I'm deforming material constant temperature, constant stress. Okay, but here suddenly we are jumping the stress, change the stress jump. So that can give you change in strain rate with respect to change in stress. So that can also give you this kind of calculations. So this kind of people do different different types of experiments to estimate type of what is the amount of activation volume. That basically tells what kind of rate controlling mechanism. Okay, is it clear about this activation volume? Are there any doubts? I think all of you are busy with something else, it seems.
No, sir.
Okay. So basically, this is actually experimental ways, okay? Because theoretically, how the activation volume is going to vary, okay, as a function of any change one of the parameters, maintain other things constant. Okay, we will come to know. Okay, we can determine the activation volume. So it's one of the ways actually both tensile test, creep test can be used to determine the activation volume of a deformation, plastic deformation. So we already know a particular, if it is a climb process with rate controlling, we should get 1 BQ. Okay, around 1 BQ we will get 1 to 10 BQ typically gives you. Okay, if I get the value 1 to 10 BQ, that means I can say that rate control mechanism is a climb process. Okay, if I want to know whether the cross slip is taking is the rate control mechanism or not, that means I should get actually 10 to 100 BQ. Okay, if the value comes to be around 10 to 100 BQ, that means I can say confidently that rate control mechanism is the cross slip is the rate control mechanism. So these are what people establish what is the rate control mechanism for a given material at a given temperature and stress conditions. Okay.
Sir,
Yes.
sir, any limitation or where exactly this equation can be used, or is it generic in nature?
These are generic. These are it's a generic in nature. Okay. This has been derived. Okay.
So, I mean, basically using such equation, we can get the, what do you call it, this activation volume, and then we can predict what is the rate controlling mechanism in particular plastic deformation.
Yes.
But there is no limitation like FCC, VC, or what material.
No. There's no limitation. That's actually kind of this is applicable to any material. Okay.
Sir, thank you.
This is one of the ways to understand what is rate controlling the plastic deformation mechanism. Okay. So this is about whatever we discuss about the thermal activation. Okay. So activation volume. There is other material also called stress relaxation experiment, which can also be used to determine the activation volume. Okay. So different approaches are available to determine the activation volume of a material when you deform it at particular conditions. So now the next thing, we are going to discuss more about the creep deformation. Okay, creep, is also what is the definition of creep? What is the definition of creep? Any idea? What is creep?
High temperature and low stress, constant stress.
Okay, is that high temperature, low stress? Is it a definition of creep? You're giving some terms, but actually it's not a definition. What is the thing actually happening? Why do you say something is getting creeping? When do you say something is creeping? So those are we are saying stress and temperature. Those are the conditions. Okay.
So if the material fails at those, then
why should material fail? Any other definition? Creep. You are given stress and temperature, but what it doesn't tell you what meaning of creeping. It's a general simple general language, English language also creeping. Somebody is creeping. Somebody is say.
So the plastic deformation of material at high temperature at constant stress, which leads to change in the dimension of material.
Okay, yeah, I think you are very close to that. Okay, creep. Okay, as far as metals, materials, as metals and ceramics also, as per materials are concerned, creep is basically defined as a time-dependent plastic deformation. Time-dependent plastic deformation. Under constant load or stress. At elevated temperatures. That's called creep. Of materials. We are talking about materials. So time-dependent plastic deformation under constant load or stress at elevated temperatures. Okay, that's called creep. Okay, so can somebody give some examples? Why do you need to study creep? Some examples, what we can see. Where creep play a significant role. Some examples. Why do you need to study creep deformation? Any examples?
Turbine blades.
Okay, turbine blades. Okay, which basically subjected to stress and also temperature. Okay, turbine blades. Where do you use turbine blades? Where do you use turbine blades?
Aircraft and power plant.
Yes. Okay, for actually aircraft engines, we also use power plant. Okay, power generation also. Okay. Yes. Any other examples? Where do you see creep? Okay. So turbine blades are made of what?
Nickel. Yeah, nickel alloys.
Yeah, not necessarily. Yeah, super alloys popular. Okay, even people also use titanium alloys also. Okay, high temperature. alloys. Okay, some of okay. So most commonly used is super alloys. Okay, yeah. So okay, super alloys are used for making turbine blades. Okay. Okay. So the creep. Okay, creep is a common even in nature also we do see. Okay, not necessarily to be a sign. Okay, engineered components. Even okay, nature we do see. Okay, creep. What is this? The left hand side in area. Any idea what is actually?
It's a glacier movement.
Which one?
Glacier movement.
Yes, yes, yeah, you are right. Okay, it's a glacier. Okay, it's a glacier. Okay, it's basically what is a glacier? What is the meaning of glacier? What is actually here? What is actually okay? It's a glacier. These all these things called glacier. Okay,
Ice formation of ice.
yeah, ice formation. Okay, so the ice. Okay, will also undergo. Okay, okay, creep deformation. Okay, there's a huge science behind. Okay, creep deformation of ice. In order to understand okay the glaciers okay how the glaciers okay will react with okay with the atmosphere. So because of glaciers we do see a lot of accidents also okay a lot of okay problems also there okay. So glaciers what happens they do undergo creep deformation. Okay, there is a I think small video which basically shows okay about the glaciers. Okay,
Hi, I'm Emerald Robinson, and in this What Is video, we're going to investigate a very unique formation of ice called a glacier. A glacier is defined as an
Hello.
Oh,
Yeah,
yes,
I think sir
uh,
has got disconnected.
yes, yes.
Yeah, let's
Hello.
Yes, sir, you are audible, sir.
Yeah, it's I think some funny thing happening here. Okay. So I think where did I think uh, left the
That
meeting
video, sir. Great video.
video. Okay. So I think yeah, not much has been changed. Okay. So just one. Are, are you able to see?
No, sir.
How about
Not
now?
yet, sir.
How about now?
No, sir, not yet.
No, sir, not yet.
It's a very strange thing happened. How about now?
Yes, sir. Now,
Okay, I think on this, I think at this slide, I think okay, my connection got lost. Okay, it's basically here. I think glaciers. Okay, will have basically have a piled up ice. So the ice undergoes some amount of okay, significant amount of plastic deformation. Okay, due to its weight and some pressure. Okay, under constant because of that. Okay, the glaciers usually move. Okay, there will be deformation. The glaciers are going to move slowly. Okay, so if the deformation is fast, the rate of deformation is fast, so the movement of glaciers will be very fast. That can lead to sudden okay burst of the thing. So that can lead to calamities okay, nearby regions. Okay, so there's a huge amount of okay research is going on to understand creep deformation of ice. Okay, but as far as this course, we what we discuss only some engineered components. Okay, creep deformation, but the principles, the mechanisms are actually are applicable to whatever materials which undergo creep deformation. Okay, so the another important okay importance of this creep deformation is basically now it's no longer I think much not many we are seeing incandescent bulb. Okay, so we do see, I think, okay, earlier nowadays there are some places people do still use incandescent bulbs. Okay, incandescent bulbs will have a filament. Okay, so why do you have to understand creep deformation of? Okay, people have spent time okay to understand creep deformation behavior of this incandescent bulb filaments. Okay, first of all, what is this filament? Okay, made of? Any idea?
Tungsten.
Tungsten based alloy. Okay, okay, tungsten with small amount of okay um, atom will be solution will be added for improving some thermal stability. Okay, why do you have to study creep deformation of this? Why do you need to study creep deformation of tungsten? Okay.
So that we can predict the lifetime of this bulb and
Yeah,
the
so where is the creep here? Where is the creep here? First of all,
Sir, it's high temperature, so
so
we'll need to
we
study
okay
that.
by giving a electrical connection it undergoes a high temperature. Okay, so what is expected temperature in the incandescent bulbs typically when you blow it? Okay, typical temperature, any idea of the filament? No. Okay, so temperature can be as high as okay 1500 to okay 2000 degrees Celsius. 1500 to 2000 degrees Celsius. If okay the material to withstand such temperatures, one has to go for a high melting okay point materials. Higher the melting point materials, okay, you can have a expected to have a higher okay creep resistance. Okay, here okay where is the stress here? That's why first tungsten is used okay as a incandescent film okay bulb filament. Where is the creep here?
so the ends are connected in that.
Yeah, just connected okay, but why should you want to go? Because I said creep is a plastic deformation, time dependent plastic deformation under constant load or stress at elevated temperature. Now temperature is there, 1500 to 2000 degrees Celsius. Okay, where is the stress here?
So while heating, it was tend to expand, but the ends are connected. So
Yeah, where is actually stress? Still doesn't tell you stress.
Sir, is
Connection
it
does
the
not.
resistance that is
No,
there inside?
no.
Okay.
It is actually tungsten is heaviest. Okay, one of the heaviest. Okay, metals. Okay, it has its own weight. Okay, weight itself. Okay, the self weight. Okay, heavy elements. Okay, it basically that gives a stress. Okay, the density of tungsten is very high. Okay, so that that self weight of the when you heat the material, the self weight can lead to increase deformation in the material. Okay, and why do you have to keep in a kind of like this environment? Okay, we have a kind of bulb glass. Okay, something is there inside. We have a filament. Okay, why do you need to have a kind of special arrangement of this kind of bulb? Anything is there inside apart from this what you are seeing? So is the filament under vacuum or just normal here, the atmosphere inside?
Vacuum, sir.
Vacuum. Okay, why do you need to maintain vacuum?
So that it doesn't get oxidized.
Yeah, okay, basically tungsten, moly, high refractory elements, high temperature, high melting point materials usually undergo easy oxidation. Okay, so in because we know that higher melting points is better good for creep resistance, but at the same time these elements, moly, tungsten, these kind of refractory elements will undergo easy oxidation. If it gets oxidized, it becomes a powdery. Okay, at that high temperature, when you heat it to 1500 2000 degrees Celsius, the tungsten, if you put it in, if you heat the material in air, it becomes a powdery whole thing. Okay, so to avoid oxidation, we have to maintain some vacuum inside the bulb. Okay, so because basically it's something to do with the heating. Okay,
This is a common household light bulb. It's simple yet brilliant. It was invented in the late 1800s, and amazingly, it has hardly changed at all. It works using a simple circuit, and the most important bit is the filament. It sits at the center of the bulb on a glass mount and is made up of a long, thin piece of tungsten metal which has an abnormally high melting temperature. Watch this slow motion footage, which is 40 times slower than normal, and you can see the circuit in all its glory. When the bulb is connected to a power supply, the electrons travel along the circuit and continuously bump into the filament's atoms, causing them to vibrate. The atoms heat up to around 2,200 degrees Celsius and boom, light. Who would have thought the humble bulb could be so ingenious?
okay, so here, at the end of the video, it's blown. Okay, because that means there is a life. Am I right? There is a specified life. Okay, it will not go beyond certain period. Every incandescent bulb has a certain hours only. It can work only certain hours. Typically, people 1000 hours typically it works. Okay, why the no? It's why it's actually stop failing. Any idea? This visual see gets fused out. Okay, after certain number of usage hours, typical of 1000 hours. Okay, most of the incandescent bulbs will get blew away. Okay, why it's getting fused out? Any idea?
The material fails at the end of the connectors and the connection is lost. Electrical
Is
connection.
is it? Are you sure? No, that's not true. Not at the end of the connections. Okay, it happens within center only. Okay, center of that filament. Okay, so this is basically creep deformation. Okay, we said the creep deformation happens at high temperature under stress. Here the stress is a weight. Okay, so each has a spiral kind of thing. It has a kind of spiral thing. So when there is a creep deformation, that means there is a plastic deformation of a tungsten wire. The tungsten wire undergoes a plastic deformation. Okay, that means there is a strain, there is a extension in the wire. After certain amount of plastic deformation, okay, the spirals whatever seeing will come together. Okay, that basically lead to fused. So typically we have this kind of turns because of plastic deformation under, okay, high temperature and, okay, self weight. We do see, okay, these things are going to, okay, because it's going to extend, okay, slowly. So that can lead to increased strain. So the wire length of wire is going to increase. Okay, after certain number of hours, okay, we are going to see these are going to touch each other. Okay, so that lead to, okay, sudden fuse out. Okay, so the creep deformation in the filament wire, okay, can lead to extended, okay, thing, because we have already given certain, okay, okay, weight. So after certain number of, okay, hours, if we are going to see these are going to touch each other, can lead to failure of the wire. Okay, so this whole thing is related to creep deformation. So these incandescent bulbs have been used more than a century. Okay, people have used incandescent bulbs more than a century. Okay, now I think we have, okay, all, okay, LED things now coming to picture because of two, okay, global warming thing. So there's a, I think people stop using, there's a regulations not to produce this kind of thing because there's a lot of heat generation happens, so that can lead to global warming. That's why I think incandescent bulbs become, okay, extinct. Okay, so I think I'll stop it here. Okay, so we'll discuss about the actual, okay, the mechanism aspects of a creep deformation and microstructure evolution, okay, during creep deformation. Okay, so the other example I think we already discussed, okay, gas turbines. I'll stop it here. Is there any doubts? Please let me. I just touched upon, okay, importance of a creep deformation. Now we'll discuss about the mechanism of creep and microstructure evolution during creep deformation. Okay. So if anybody has doubt, they can stay back. Others can leave.
Thank you, sir.
Thank you.
Sir,
Yes.
sir,